Okay, so we're going to look at superposition of point vortices. We've got our setup shown here. We've got a vortex of circulation kappa at delta 0. So y coordinate 0, x coordinates delta. We've got a circulation minus kappa vortex at minus delta. So I'm just going to write down the stream function in total. Point vortices are irrotational, except at the point themselves. Therefore, everywhere except the point themselves, we have a velocity potential. Because we have a velocity potential, we can superpose velocity potentials. Now, what I'm talking about here is a stream function, right? The principle of superposition will also apply to stream functions. It'll also apply to the velocities themselves, but you have to be more careful when you're superposing velocities because each velocity is a vector component and you have to do vector addition, right, to get it right. Instead, if you're dealing with a stream function or a velocity potential, they're scalar functions, so you can just add them up naturally. So I'm going to write down psi, the stream function, for this flow. Psi total equals minus kappa delta pi 2 pi log brackets x minus delta squared plus y squared half plus kappa on 2 pi log x plus delta y squared half, like so. We could simplify this. The only simplification that I think is reasonably worthwhile is taking out the half here using our log law, right? So that can come down there. Okay, so once we've got this, we've got our stream function. Because we have a stream function, we can use the definition of our stream function to obtain velocities. So remember that du equals d psi dy, v equals d psi dx, and there's minus sign. So we can evaluate the velocities everywhere just by differentiating psi. So let's differentiate psi and find u. So I've actually swapped the order here. I'll do this one first, draw it here. So 2y, right, coming from the argument. Derivative of log is 1 over the argument, x plus delta squared plus y squared, like so. Minus this one here, because the minus sign's there, 2y x plus delta squared plus y squared, like so. You can see very quickly that at the centers of the vortex, of each of these vortices, say x equals delta, y equals 0, right? The u is 0. U equal, because y is 0, right? That's pretty obvious. And x equals minus delta, y equals 0. That's the other vortex, u is still 0. So that tells us that there's no flow in this direction. There is 0 flow this way. That's what we've deduced by computing those velocities, right, at the vortex centers here. So let's now compute V. So V, we've got to differentiate again. We're just going to get more. It's going to be pretty similar, right? So I'm just going to skip ahead. Here. Now, this is quite good. This is interesting because now when we substitute in our vortex centers, x equals delta, y equals 0, we get the following. V equals kappa 4 pi 4 delta, right, because that's going to give me 2 delta, over 4 delta squared. Oops. Oh yeah, 4 delta squared, sorry. So brackets. Plus 0. Minus, well, that's going to give me a 0. So we now at this vortex center have some positive v velocity. What happens at the other vortex center is there's also a positive v velocity. So what this suggests is that these vortices are going to travel upwards, right? There's a velocity in this direction. Like so.